In this videotape, we will introduce the idea of a logarithm and discuss the relationship between logarithms and exponents. Let's start with a formal definition. The expression y equals log of x with a little subscript of b here, which is read y is the logarithm of x to the base b is equivalent to x equals b to the y power, where b is some positive number and it's not equal to 1. Okay. So what I'm saying here is that y equals the log of x to the base b. This is equivalent, this symbol means is equivalent to x equals b to the y power, where b is a positive number and it's not equal to 1. So what I'm saying here is that what is a logarithm? The logarithm of a number x to the base b, the logarithm, which in this case is y, is the power that you have to raise the base to get the number. The logarithm of a number to the base b, y, that's the logarithm of the number x to the base b. Y is the power that you have to raise the base to get the number. So a logarithm is, first of all, it is a power, it is an exponent. Okay, the logarithm of a number to the base b is the power that you have to raise the base to get the number. Let's look at some examples. Let me just rewrite the definition. Y equals the logarithm of x to the base b if and only if x is equal to b to the y power. Just remembering that b is a positive number, b is not equal to 1. Okay. Suppose I want to figure out the log of 8 to the base 2. I claim that the log of 8 to the base 2 is 3, since 3 is the power that you would have to raise the base, which is 2, to get 8. Okay. Because 8 is equal to 2 cubed, because 3 is the power that you would have to raise the base 2 to get 8. The logarithm of 8 to the base 2 is 3. Since 3 is the power that you would have to raise the base is the subscript here. 3 is the power that you would have to raise the base to get the number 8. Okay, let's try another one. The log of 9 to the base 3. I claim the log of 9 to the base 3 is 2, since 2 is the power that you would have to raise the base, which is 3, to get 9. And let's look at this. The log of 1/8 to the base 2. So what I'm going to write here is the power that you would have to raise 2 to get 1/8. Okay. Remember that 1/8 is really 1 over 2 cubed, or 2 to the minus 3 power. 1/8, that's 1 over 2 cubed, is 2 to the minus 3 power. So the logarithm of 1/8 to the base 2 would be minus 3, since minus 3 is the power that you would have to raise the base to get the 1/8. And we can also reason the other way. If I write down that 125 is equal to 5 cubed, can you write down an equivalent expression in logarithms for me? I'll give you a moment to think about that. Okay, if 125 is 5 cubed, 5 times 5, that's 25 times 5 is 125. I want you to write down an expression in logarithms which is equivalent to that. Okay. 3 is the power that you would have to raise 5 to get 125. So we could say that the log of 125 to the base 5 is equal to 3. Since 3 is the power that you'd have to raise the base to get 125. Of course, you could just match this up in this way. In other words, you would say that here x is, in other words, x is 125, b is 5, y is 3, and if x is b to the y, this is equivalent to y is the log of x to the base b. So then you get that 3, which is y, must be the log of x 125 to the base 5. Okay, you can always resort to this definition, but it's helpful if you sort of, in other words, understand what it's saying. The log of a number, okay, the log of 125 to the base 5 is 3 because 3, the log is the power that you'd have to raise the base to get the number. Okay, let's do it the other way. Instead of me giving you the right-hand side here, the power, let me give you the left-hand side, and you write it down in terms of logarithms. It is true that 4 is 8 to the 2/3 power. Excuse me. It's not quite what I wanted to do here. Okay, let's try it this way. The log of 4 to the base 8 is 2/3. I would like you, I claim that's true, I'd like you to write down the equivalent expression in powers. The log of 4 to the base 8 is 2/3. You write down the equivalent expression in powers. I sort of gave it away already, but work on that. Of course, you can match it up, and you can say y is 2/3, b is 8, and x is 4, so that you get that 4, which is x, must be b to the y power 8 to the 2/3 power. Eight to the 2/3 power, by the way, means it's like 8 to the 1/3 power squared, or the cube root of 8 squared. The cube root of 8, that's 2, squared is 4. So 8 to the 2/3 power is 4. It's the cube root of 8, which is 2, squared, which is 4. The log of 4 to the base 8 is 2/3. Okay, since 2/3 is the power that you'd have to raise 8 to get 4. Okay, let's try some more examples. Okay, in all of these examples, something is sort of left out, and you've got to fill it in. The log of x to the base 5 is 2. Because in each case, you have to solve for x. I just want to remind you that y is the log of x to the base b is equivalent to x equals b to the y. Once again, b is positive, but not 1. The reason we rule out this b equal to 1 business is that 1 to any power is just going to be 1, so it wouldn't make any sense in this context. Okay, now, I want to figure out what x is. So I say here, the log of x to the base 5 is 2. This must be equivalent to saying, okay, if the log of x to the base 5 is 2, 2 is the power that you have to raise 5, the base, to get x. X must be 25. Let's look at that here. X is x, b is 5, y is 2. So b to the y power means 5 to the 2 power. That's x, that's 25. The log of x to the base 5 is 2. If 2 is the power that you have to raise 5 to get x. Okay, let's try another example. Log of 81 to the base x is 4. Okay, don't be upset by the fact that I'm using the same x. X here is playing the role of b. Okay, the log of 81 to the base x is 4. Okay, this would make sense if it were true that 4 with a power that you would have to raise the base x to get 81. In this case, b is x. Okay, the base is x. The number whose log you're working with, what's x here is 81. So you get 81 is b to the y. 81 is x to the 4. The right-hand side here, that's y. The log of 81 to the base x is 4. If 4 is the power that you'd have to raise the base to get 81. Remember, the log is a power. The log is an exponent. The title of this tape is Logarithms and Exponents. Logarithms are exponents. Okay. It's the exponent, the power that you have to raise the base to get the number. Okay, if x to the 4th is 81, then x would be the 4th root of 81. X could be, strictly speaking, plus or minus 3. In other words, 3 is a 4th root of 81, so is minus 3. So you'd say x is 3 or minus 3, but you would reject the minus 3 because x is a base. And remember, we're saying the base has to be positive. So you'd solve this equation. You'd see that x could either be 3 or minus 3. 3 to the 4th power is 81, and minus 3 to the 4th power is 81. But bases, remember, x is a base, have to be positive by definition here. So x is equal to 3. Okay, let's try another example. The log of 9 to the base 27 is x. Here, okay, the unknown is the, in a sense, the left-hand side. It's really the y. The log of 9 to the base 27, this is equivalent to saying that x is the power that you'd have to raise the base to get 9. The log of 9 to the base 27 is x. If x, which is this log, x is the power that you raise the base to get the number. And we're trying to solve for x. Okay, now the trick in solving an equation like this for x is to try to get both the left and the right-hand side, okay, in terms of the same base. On the right-hand side, we can say 9 is really 3 squared. And 27 is really 3 cubed. So we have 3 cubed, okay, to the x power is 3 squared. Now, 3 to the 3 to the x is 3 to the 3x power is 3 squared. And once you get it like this, okay, two things are equal, and they have the same base, and their powers must be equal as well. If 3 to the 3x is equal to 3 to the 2, the powers must be equal as well. The only way 3 to the 3x is going to be equal to 3 to the 2 is if 3x equals 2 or x equals 2/3. And we can check this. Is it true that 27 to the 2/3 power is 9? (27 to the 2/3 power). If the answer here is 2/3, and 2/3 is the power that you'd have to raise 27 to get 9. 27 to the 2/3 power, you can think of this as 27 to the 1/3 power squared. The cube root of 27 squared. The cube root of 27, that's 3 squared, is 9. So it checks out. Okay, now, I would like to graph the logarithm function with a particular base substituted in. We can, use any positive number other than 1 for the base. Let's say we want to graph y equals log of x to the base 2. It's a function of x. We'd like to graph it. Okay, we say, well, I don't know much about the log of x to the base 2, but of course you know its equivalent here. Log of x, y equals log of x to the base 2 is equivalent to x equals 2 to the y power. So if this is equivalent to this, we can sketch this one, which is an exponential function, which we have already sketched something similar to this. Okay, in the previous videotape, we sketched y equals 2 to the x instead of x equals 2 to the y, but we should be able to handle this one as well. And by sketching this, you are sketching this, which is equivalent to it. Okay, so let's make a table of values for ourselves. Okay, if you have x equals 2 to the y and you're working with that, it seems to make sense to let y take on different values and figure out what x is. Okay, because it's x equals 2 to the y power. So let's let y take on different values. Let's let y be, say, -2, -1, 0, 1, 2, 3, 4, so on. Each case, x is equal to 2 to the y. So x is, for here, 2 to the -2, 2 to the -2. Here it'll be 2 to the -1, 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4. Well, 2 to the 4th, that's easy enough. 2 times 2 times 2 times 2, that's 16. So we know 16, 4 is a point on the graph of this function here. 2 cubed, well, that's 8. 2 squared, that's 4. 2 to the 1, that's just 2. 2 to the 0 is 1, remembering our rules for working with exponents. 2 to the -1 is, of course, 1 over 2 to the 1, or 1/2. And 2 to the -2 is 1 over 2 squared, or 1/4. We now have several points on the graph of x equals 2 to the y, and of course, that means they're also on the graph of y equals a log of x to the base 2. Let's plot them. Okay, so the x values go up to about 16. Well, we can just skip this one. We'll go up to about 8 so I can get them on here. And then the y values are running from, say, -2 to 3. Let's see the points that we need. Okay, remember, these are the x's and these are the y's. We're going to plot the point 8, 3. 8 over 3 up. we're going to plot the point 4, comma 2. 1, 2, 3, 4, up 2. And we're going to plot the point 2, comma 1. 2 over 1 up. And then 1, comma 0. That's where the curve is going to cross the x-axis. Okay, after 1, 0, we're going to plot 1/2, comma, minus 1. And then 1/4, comma, minus 2. And so on. Now, what would happen if you let y take on, say, more negative values here, like minus 3, minus 4, and so on? You'd have 2 to the power. So, for example, if y was minus 5, you'd have 2 to the minus 5, which is 1 over 2 to the 5th. X would be like 1 over 32. In other words, the x values would be getting very, very close to 0 as the y values get very negative. The curve, in fact, has an asymptote. The negative y-axis is an asymptote for this curve. It gets very close to, but never quite touches it. It gets like this, gets very, very close, continues that way. And the curve is it's increasing like that. Looks something like this. This is the graph of y equals the log of x to the base 2. We made use of the fact that x equals 2 to the y to get the points, but of course it also works this way as well. If you would have said, for example, if x is 2, I want the log of 2 to the base 2, the power that you have to raise 2 to get 2, and the answer, of course, would be 1. It's just easier to work with the other form. Okay, but these are equivalent, so we've got the points for this graph. Some of you may remember that in the last videotape, we sketched the graph of y equals 2 to the x. Okay, and those of you who do remember it looks something like this. This was y equals 2 to the x power. You could make a little table of values to figure out what's going on. Here we let the x take on the different values. For example, x could be minus 2, minus 1, 0, 1, 2. Y would be, if x is minus 2, y is 2 to the minus 2, or 1 over 2 squared, or 1/4. For 2 to the minus 1, you get 1/2. When x is 0, 2 to the 0, that's 1. When x is 1, you get 2 to the 1. And when x is 2, you get 2 to the 2, which is 4. Basically, what has happened is these points are found by reversing the x and y coordinates of these points. Whereas over here, we have the point 0, 1 to plot. Here, we plotted the point 1, comma 0. Okay. We have reversed the x's and the y's. If we look at the graph of y equals 2 to the x, and on the same set of coordinate axes, we put on y equals log of x to the base 2, or x equals 2 to the y. X equals 2 to the y looks like this. Let me sort of dot it in. This is the graph of x equals 2 to the y, which we've just sketched. And we see that there is some kind of relationship between them. Y equals 2 to the x had the negative x-axis as an asymptote. X equals 2 to the y has a negative y-axis as an asymptote. Let me explain what's going on here. If you take a point, let's say a point 5, comma 1, 1, 2, 3, 4, 5, 1, and you reverse the x and y coordinates, you get the point 1, comma 5, which would be here. This is 1, comma 5. If you draw in the line y equals x, which is the 45-degree line, the line which bisects the first quadrant here, these 2 points are reflections of each other through the line y equals x. In other words, if you were to connect them by a straight line segment, the line y equals x, the 45-degree line, bisects is the perpendicular bisector of this line segment. Okay. By switching the x and y coordinates, 5, 1, making it 1, 5, you get a point which is located on the other side of the line y equals x, sort of the same distance away. Let's try another one. 3, 2 is over here. The point 2, 3 is over here. Also, sort of the same distance away on the other side of the line y equals x. If switching a point's x and y coordinates, in a sense, reflects the point through the 45-degree line, then taking an entire curve, like x equals 2 to the y, and letting x be y and y be x on the entire curve, giving you y equals 2 to the x, in a sense, it reflects every single point on the graph through the 45-degree line. So the graph of x equals 2 to the y is a reflection of the graph of y equals 2 to the x through this 45-degree line. Let's go over the logic again. Taking a point like 5, 1 and reversing its x and y coordinates on just that one point has the effect of reflecting that point through the 45-degree line. And doing it to another point, 3, 2, the same thing. If you take an equation, an entire equation like y equals 2 to the x, and you replace y by x and x by y to give us x equals 2 to the y, you have, in a sense, reversed the x and y positions for every single point on the graph. Okay? And the graph of this reversed function, okay, if this is y equals 2 to the x, the graph of x equals 2 to the y can be found by reflecting the graph of y equals 2 to the x through the 45-degree line. You'd expect this to be a reflection of this. Sort of like the line y equals x is acting like a mirror. This is a mirror reflection of this. Okay, let's try some more examples. If you didn't understand this last thing, I mean, don't worry about it too much. The important thing here is that we could sketch this new function, this logarithm function, y equals log of x to the base 2. We could sketch its graph by making use of the equivalent representation with exponents and plotting points and get the graph, okay, like that. And it's related to the graph of y equals 2 to the x, which we sketched in the last lesson. And we see that this relationship is not a coincidence. There is a very important reason why these two are related, why they are reflections. Okay, but don't worry too much about that if it upsets you. The important thing is that one can sketch the graph of a logarithm function by using the definition in exponents. Okay, let's try some more examples. In all of these, I want you to remember, you always keep in mind your basic definition of logarithms. That is, y equals log of x to the base b is equivalent to x equals b to the y, where b is a positive number, but not 1. Okay, and I'd like to work out some examples. I would like you to simplify the log of 81 to the base 3, or see if you can tell me what this is equal to. Okay, we can, wherever the question mark is, we can sort of replace that by a variable. Let's say we're trying to find x or y, whatever. You can call it y. If you're trying to find y, you can just, trying to find the log of 81 to the base 3, you can sort of just match it up here. That's y. We're trying to find y, and we say, well, the log of 81 to the base 3 is y if 3 to the y is 81. The log, after all, the log of a number to a certain base, the log, which in this case is y, is the power that you'd have to raise the base to get the number. So 3 to the y is 81, and we want to figure out what y is, and we make use of the fact that if we can get the right-hand side also in terms of a base of 3, we'd be able to equate the exponents. And it turns out 81 is 3 to the 4th power. 3 times 3 is 9, times 3, 27, times 3, 81. Since 3 to the y is equal to 3 to the 4, then y must be equal to 4. Okay, so the log of 81 to the base 3 is 4, since 4 is a power that you'd have to raise 3 to get 81. Okay, what about the log of b to the base b? The log of a number, okay, to the base, and the base and the number are the same. We want to work that out. Okay, let's call this y. Remember, the log of x to the base b is y. This is equivalent to x equals b to the y. So if the log of b to the base b is y, that means y must be the power that you'd have to raise the base, okay, to get the number, which is also b. The log, from here we go right to this. If the log of b to the base b is y, then y is the power that you'd have to raise b to get b. Well, this is very simple to work out. B to the y is equal to b to the, obviously, the 1. B is just b to the 1. The bases are the same, so the powers have to be the same. Y equals 1. So we get that the log of b to the base b is 1. And this is always going to be true. Okay, if you have the log of a number to a base which is the same as that number, okay, that has to be 1. Because after all, what power do you have to raise the base to get the number? Obviously, the first power. B to the 1 will be b. Okay, how about this? We want the log of 1 to the base b. Let's say the log of 1 to the base b. We're looking for that. Let's call that y. Well, you could just leave it like that. That's going to be y. Remember that the log of x to the base b is y if and only if x equals b to the y. So the log of 1 to the base b will be y, calling this y, if and only if x, which is 1, equals b to the y power. Y is the power that you'd have to raise the base b to get 1. So 1 is equal to b to the y. And we realize that what power do you have to raise b to get 1? Y must be 0. Okay, b to the 0 is 1. Take a non-zero number to the 0 power. That'll give you 1. Okay, so the log of 1 to the base b is 0. Of course, if you could reason this out, okay, in your head, fine. Okay, we see two important relationships. The log of b to the base b is 1. Okay, simply b to the 1 power has to be b. The power that you raise b to get b is 1. B to the 1 is b. The log of 1 to any base is 0. Okay, this means, by the way, that all logarithm functions, okay, of this form will have 1, 0 as a point on their graph. Okay, we sketched a few moments ago the log of x to the base 2. And we saw that it went through the point 1, 0. Because the log of 1 to the base 2 is 0. Okay, this is because b to the 0 power is going to be 1 regardless of what the base here is. Okay, so all these logarithm functions are going to go through the point 1, 0, have 1, 0 as a point on their curve. The x-intercept will be 1. The log of 1 to any base is 0, since b to the 0 is 1. Okay, let's finish off with one more example, but it's going to be a doozy. Okay, I want you to simplify the following expression.